Hello to everyone, my name is Roberto Scheffel and I will present the paper Data Confidence Applied to Wind Turbine Power Curves. This paper is a collaboration between the Hardware-Software Integration Lab of the Federal University of Santa Catarina and AQ Tech, an enterprise specialized in developing supervising systems for power generation plants. Power curves are used to verify the health condition of wind turbines, as they depict the relation between the wind speed and the power generated by the unit. This relation can be obtained by a variety of forms, as linear, polynomial or logistic regressions, clustering-based or machine learning techniques. This graph illustrates some power curves from different models of wind turbines. The height, the inclination, and the start and end points of the curve are specific to each model of wind turbine. The parameters that define a power curve function are the cut-in and the cut-out speeds that define the minimum and maximum wind speed under which power is generated. Wind speeds over the cut-out make the system be stopped to prevent damages. The maximum speed defines the wind speed at which the generator produces the maximum energy, defines the top limit. Stronger wind do not produces more energy, and the slope defines the angle or growing speed of the power curve function. A power curve model tries to verify if the relation between the current wind speed and the reported energy production fit to the power curve function. If the produced power is not in line with the wind speed, alarms can be set, indicating something is wrong with the wind turbine. The objective of the solution presented here is to avoid false alarms or wrong analysis when faulty sensor readings arrive from the field. It will also be a demonstration of the use of the delicious IoT platform workflow mechanism that allows data to be processed as it arrives from the sensors in the field. Some previous works tried to diminish false alarms on power curve models and are presented now. Pettit et al. Used a Gaussian process to fit a nonlinear function on clean training data. Afterwards, outliers were identified by a confidence interval based on a Gaussian probability distribution. Ie et al. Removed outliers by identifying them by timing and value range characteristics, defined through a couple-adjoint distribution function. Song et al. Proposed the use of a subtype of recurrent neural networks, called gate recurrent unit. It uses windows with the n last samples of scaled data to detect and remove outliers. Finally, Yang-Hu et al. Modeled the power curve using a three-dimensional coupled space. Possible values were split into 5 regions, and outliers were identified by the distance to the presented line. Nisha's IoT platform architecture is displayed in this picture. Data periodically collected in the field, power turbines in this example, arrive as time series. If a series is created with a workflow ID, data points are first processed by the workflow components, the process 1 to n shown in the picture, before they are stored at the database. The workflow's components can use several tools and models to process the data, and can also generate alternative series, which are processed data, not raw data, and are stored separated in the database. They can also generate log entries or send notifications with different severity levels. The confidence attribution schema applied in this work uses the data correlation to verify the correctness of sensors data. To do this, predictors, in this case artificial neural networks, are used to calculate the expected sensors value. These predictors are built and trained in advance, and the mean absolute error, or MI, is obtained in the training process and used as a parameter in the confidence attribution process. This makes good prediction models show smaller tolerance margins. Other parameters to be defined are beta, that defines the maximum distance between read and predicted values in terms of mi, alpha, that defines the velocity at which the confidence on the read values drops as the difference from the predicted value increases, and the gamma parameter defines the minimum confidence that a data piece has to show. If the confidence value is lower than gamma, it is replaced by the prediction. The function f of v and v hat defines the confidence attribution. If the absolute difference between v and v hat is lower or equal than beta times mi, then the confidence is 1, or 100%. Otherwise, the distance that exceeds the full confidence interval is divided by the mi multiplied by alpha and subtracted from 1, making it decrease to 0 as the distance between the values, or the error, increases. The mi is just the mean from all absolute errors obtained in the training process, as shown in the second function definition shown here. The prediction models, artificial neural networks, used in this work were built over a dataset of 8 wind turbines at close positions in the wind farm. From each wind turbine, the wind speed and the generated power measurements were used, making available a total of 16 input variables or features to be used by the predictor's building process. From this dataset, for each sensor, an artificial neural network was built, using as input the 6 most related sensors' values. These features were selected using the Mutual Information Gain Analysis function from the sklearn toolkit library. This graph shows the wind speed values read and predicted from a specific wind turbine. The red crosses show the confidence assigned by the algorithm. Almost all readings are okay, showing that the predictor has a good accuracy. This other graph shows the read and predicted values of the generated power of the same wind turbine from the previous graph, also with high confidence of almost all points. When injecting errors of type peak, stuck at, or noise, the confidence attribution mechanism starts to lower data confidence. At the worst case, when distant from the correct predicted value, the confidence drops to 0. The red circle shows a place where a gap between the values is large enough to make the confidence drop. This illustrates how the confidence attribution mechanism works. The power curve model used in this work is the one proposed by Villanueva and Feijó. This function divides the maximum power by an exponential function that increases as the wind speed increases, with a saturation point determined by the slope A and by the parameter B, that is the mean value between the cut-in speed and the maximum wind speed. The parameters values that make the power curve model function best fit the data reported by the wind turbines must be found. So, the best values for the power curve model were searched by exploratory simulations, varying the parameters in the shown intervals and steps. The best values for the power curve fitting obtained for every wind turbine are shown in the lower table. The parameters that show some variation between the wind turbines were the maximum speed and the slope. All other parameters have the same value for all turbines. After building and training the predictors and finding the optimal parameters for the power curves, the workflow at the IoT platform for the proposed solution is shown here. The time series sent by the wind turbines will be processed first by a simple outlier removal algorithm. Knowing the statistics from previous data samples, the values that are distant from the mean more than 3 times the standard deviation are discarded as outliers. If not marked as discarded, the next step is to run the confidence attribution algorithm. If more than n sequential samples of the same sensor present a confidence under a threshold, then a notification is generated. Only if the data point has confidence over the defined threshold, then the power curve model is applied. Once more, if several sequential values fall outside the power curve model, then a notification will be sent. At the end, the data point is inserted in the database. This graph shows the power curve model of one of the wind turbines. The blue line is the power curve defined by the equation. The green lines define the tolerance around the power curve in which a value is still considered correct. This region is represented by the yellow points. The red points are readings that do not fit the power curve and therefore are considered incorrect. This graph shows the result of the confidence attribution algorithm. All data points with confidence under 100% are plotted in gray. Much of the points previously classified outside the power curve model were marked here as low confidence values and ignored by the power curve algorithm. The next step of the experiment was the evaluation of error injection in wind speed data points. The outlier remover was able, again, to remove only the values on the extremes of the data interval, marked in black in this graph. As an observation, the negative values of the wind speed are due to the error injection mechanism used in the experiment, that blindly adds or subtracts a random quantity to the original value, without reasoning about the domain. When thinking about a sensor, a hardware failure could make the sensor report negative values. These do not invalidate the results. Now, this picture shows the power curve after the outliers and low confidence data points elimination. Some distant points remained, but with a noticeable reduction. As the power curve model employed is one of the simplest, we can agree that a model that provides a larger tolerance interval will classify correctly more data points. Here we can see the number of false positives removed by each technique alone and by the combination of both. In the left half, the raw data from the dataset was used. On the right half, errors were injected on the wind speed of the first turbine, WT1. The graph also shows that turbines 1, 4, and 6 have the most faulty data points. This can show the need to make an inspection or calibration on these sensors. This table shows the results when using different levels of confidence to classify a data point as faulty and discard it. Obviously, requiring 100% confidence gets the highest reduction on false alarms, but it will also discard more good points with false positives. As previously shown, wind turbine 1, 4, and 6 got the greatest reduction on false positives. The main results of this work are: the proposed workflow architecture to process incoming data at the Lich's IoT platform has been proven useful for online data analysis. The data confidence mechanism can be used to remove faulty data that causes false alarms. Outlier removal, based only on the standard deviation criteria, is only able to discard values at the edges of the value ranges. And the confidence attribution mechanism brought an improvement on false positive reduction between 5 and 31%, as well as a small increment on the overall model coverage. And so we finished the presentation. Thank you for your attention, and I will be available to answer any questions. Thank you.